This is lecture 26 in a course on single agent search. And in the last few videos, we've started to look at pattern database heuristics. And these aren't the only type of heuristics we're going to create. We'll look at a few other types, but we're going to delve a little bit more deeply into pattern databases because there is quite a bit that can be done here with pattern databases in practice. And so, or a lot of enhancements that can be done to make them be very effective in practice. And so what we're going to look at in this lecture or this video is additive pattern databases. And what I want to do is I'm going to show what is going on in a regular pattern database. And then we'll talk about how we can get it. So if in the past lecture, we were looking at if I had multiple pattern databases, and for instance, if you look at the online demo that's being used, you can see that when I have multiple pattern databases, I'm taking the max of each of them. And in this lecture, we're going to show how we can actually add them together by changing the way that we compute the heuristic. And additive pattern databases are much more powerful than regular pattern databases, and therefore they are can be more effective depending on your state space. And the last thing we'll see is there's actually an equivalence of additive pattern databases to the Manhattan distance heuristic. And so this is going to get us back to Manhattan distance and perhaps more. We described it quite a few lectures ago. We looked at the Manhattan distance could be seen as an abstraction of the state space by abstracting some of the operators. The distances in that case we would have gotten would have given us Manhattan distance. But the problem is it was still going to be an edge supergraph, and there's some issues with actually trying to build and store the heuristic in that case. And so when we look at it from the perspective of additive pattern databases, we'll be able to get rid of all those problems and just be able to directly build heuristics. Okay, and so let's look at a pattern database and let's just think about what happens here. So in a normal pattern database, let's just say I'm going to keep 0, 1, and 2, and then everything else is a star here. Okay. And what happens when you do a regular additive pattern database is we're going to take the goal. So this is the goal state, and we would search outward from the state in the backwards direction, basically. This is an undirected state space, so this is fairly easy to do. But we'd search out in the backwards direction, generating states until we've examined all states in the abstract state space, which is here. And then if we think about, I might have a real state. In fact, remember that there's many real states in the world that will correspond to abstract states that basically correspond to all possible assignments of actual tiles to the things that we've turned into stars. Okay. And so what we might have, for instance, is we have a state here, which is 0, 1, sorry, I don't want the 0 there. We're going to make star 1, 2, 0, star, 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 star. Okay, so this is a state that in the abstract state space is exactly one move from this state because I move the blank up, and then I'll get to the goal here. But there are in practice, of course, many, many possible states that could actually be here, right? So the actual state I could be in, I'm not checking the parity here, so we'll just ignore the parity. One actual state I could be in would be 3, 1, 2, 0, 4, 5, 6, 7, 8. And this state gets a heuristic of 1 because in this state, we are exactly one step away from the goal. And therefore, this state must have a heuristic of 1, which is admissible. And therefore, that's the heuristic we get there. But there is another state here, which would be 8, 1, 2. So let's put our lines here. 8, 1, 2, 0, 4, 5, 6, 7, 3. And these two states, if we think about the abstraction, they're both identical with respect to the abstraction. The 0 is in the same place and the 1 and 2 are in the same place. But this state is obviously much farther because I've got to get the 3 over here in order to finish solving this problem. Okay, so what that's showing me is that there are Like there's many states, abstract states here that correspond to a single state here. And when I actually run my pattern database here, I am saying that, look, whatever this star is, I am going to move it over here. It's going to make me cost 1 away. And then what's going to happen is that I'm going to end up in, in practice, I'll be in one of, let's say, one of these 2 states or one of many others. But then this is going to correspond to like moving this 8 down here. And so whatever this tile is, I still count that I move that tile over there. Even though this tile is a star tile, it's still a tile that exists within the state space. And this is a key idea because these tiles still exist. When I move them, they still have cost 1, and I still compute how I move them around the world. And now there's another way that we can do this, which is we could, for instance, not count the moves of the star tiles. And in particular, if I have 2 pattern databases, so let's just think if I had another pattern database here. And this pattern database is going to be, well, I'm going to do another state here. So let me draw the pattern over here. So this pattern, I'm going to keep the blank here, and then I'm going to have 3, 4, 5, and let's make all of the rest of these be stars. Okay, so when I go into, just correspond to this abstract state here, the same thing. So now what would happen here, if I look at this next state, I'll actually get different states depending on which one of these states that I'm in, right? Because this state here would correspond to 3 star star 0 4 5 star star star. And in this state, we would clearly say we're 1 step away. And this state corresponds to star 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 0 4 5 star star 3. Okay, and what I see here is actually this state, because it is in this heuristic, is captured as being, this state is captured as being 1 step away from the goal. And this abstraction is also 1 away, and we take the max of those, and we would get 2 away. And so here we would see that this is exactly the correct heuristic for this state, and this is exactly the correct heuristic for that state. And therefore, I can't take my 2 heuristics here and add them together, because doing so would count, it would basically count this 1 here twice, and we'd get a heuristic that overestimated. And now look at this state over here. What we see is, well, here I'd say, look, I need, and especially if I'm thinking about where the blank is, I'm going to need quite a few moves to get the 3 over here and to get the 0 into the location where I need it to be. And so we would capture here. So just by using 2 pattern databases, this state is captured perfectly by just one of these pattern databases. This state is not captured very well by this pattern database, but it is captured fairly well by this pattern database, or this one here. And so the abstract distance from here, when I actually get to this state here, sorry, where the 3 is down in the corner, I'm able to know that it's going to take quite a lot of work to get the 3 down to here and to get the blank back into the corner. Okay. So we can use the max of 2 pattern databases and capture these dynamics. But if I could add the heuristics together, it might be even better. And as I said, the problem here is when we look at what is going on here, in this state, we return a heuristic of 1 because I need to move the 1 star tile down here. And in this state, we have a heuristic of 1 from this pattern database because I need to move the 3 down. And so if I'm going to want to add these together, what I have to have is I have to be able to say the costs that are calculated in this first pattern database are not calculated as part of the second pattern database. And the way that we can do this is that we're basically going to partition our cost space between our pattern databases. And we can actually do this in almost any way that we want, but there's some ways that are much more effective than others. So what we're going to do is we're going to only assign every tile to a single pattern database. And when we assign a tile to a single pattern database, we are only going to count the cost of getting that tile into the goal from that single pattern database. Okay, So this is the example of, these are non-additive. We're just having to take the max, and here, so this is our topic for the day. This is the old method we're using. And what we're looking at here is additive. And what we only want to do is when we do the breadth first search, only count the cost of actions on tiles in the pattern. Okay. So what happens here? So if I go back and I want to use exactly these same states again, and I look at this state space right here, the action that I have here that I need to bring this state to the goal state is to move the star down and move the blank up. Now we never count the actions of the blank, we only count the actions of the tiles. And because this star is not a tile that is part of the pattern, then I'm not going to count it. So in a regular PDB, then this state, I'll just move it, put a copy of it down here. So in a regular pattern database, here, the heuristic of this state is going to be 1, because I need one action. In particular, I'm going to have to move the one star tile down to this middle row in order to get the 0 blank into the correct location there. But in an additive pattern database, because I don't count the actions of these tiles, then I'm going to say here that this state has a heuristic of 0. Okay. And when I do that, for every set of tiles, I'm going to have I'm only going to calculate what does it take to get those tiles, ignoring all other tiles into their location. So basically what I do with an additive pattern database is I have a custom, not only, I'm going to do the same cost that I did before, but I'm going to have a custom function, cost function, which is going to say the cost of an action depends on the pattern that we're using in the pattern database, or my domain abstraction. And if the action involves a tile which is part of the abstraction, then I will count that. Otherwise, I won't. And what that means for my breadth first search is that my breadth first search is going to have to deal with 0 cost actions within the breadth first search. So I may expand a state, I may generate successors, and then the successors of those states may be additional successors. There may be additional successors of that state which are also of 0 cost. So what that means is that, for instance, in a state like this, I'm able to move this blank around these star tiles here, and I could move the blank all around here as much as I needed to with no cost. And so if you think about that, that means the blank can get to actually every star tile here at 0 cost. And in another way, then, this is sort of like setting up the state space to just say, look, what I'm going to do is I'm going to say that I have a 1 and a 2 here, and everything else in the state space is a blank. Right? So all of these are just blanks. And what that means is that, if I look at this state space, this state right here, in the regular world, if I want to move the 2 down, I have to think about moving the 0 over, the 0 over, and then moving the 0 down up to get the 2 to move down. But in the additive state space, these stars don't cost me anything to move. So I can move the blank over, and get the 2 to move down, which would be equivalent to just allowing me to have a blank sitting right here and move that 2 down. And I could do that in just one action. It would happen immediately. Now, this gets into sort of this implementation issue. Do I need to implement a sliding tile puzzle where I have, only some tiles there and everything else is blank, and now I have to deal with lots of blanks there? You can do it that way, or basically you have to keep track of where the blank is as it's moving around the state space, but you don't count the actions of the blank. And In one of the immediately next videos, I haven't decided exactly in the order I'm going to present this material after this, but we will be talking about compressing away the blank. So typically what happens when we're building additive PDBs, we keep track of where the blank is, we keep track of where these tiles are, but the actions of the blank don't cost anything. And so the blank can move to any of these locations here without incurring any cost in the state space, which means then like I could move the 2 down. Now, it's not quite equivalent to allow the blank to be anywhere and to allow all these tiles to be the blank versus having them cost nothing. And the reason would be, in fact, you'd even see this if I applied this action. If I just do 1, 2, I can basically have a blank be here. So this is my 0 tile. And if I know that the rest of these are stars, but I just don't count their action, I still know that there is some cost to get the blank out of the corner. Like if the blank is in the corner, I have to do some work to keep the 1 and 2 in the position they're in and get the blank out of the corner and put it somewhere else in the state space. So, there actually is some loss we would have if we treated everything as being the blank. But mentally, we can think about that's sort of effectively what happens. And the difference here is when we have a set of tiles that basically partition off. So we have 2 parts of the state space. If the blank is on one and the blank needs to get to the other, then there is some gain we have in representing that the blank is actually here, and it's going to take some work to keep this same configuration of tiles, but get the blank to be somewhere else. Okay, maybe that's getting a little bit into the weeds, but this is the idea of an additive pattern database, and the idea here is I'm going to take my puzzle. I'm going to keep the blank, and I'm going to keep exactly 1 more tile. And the reason why I have to keep the blank actually is because the preconditions of the move operator is I care about where the blank is and I care about where a tile is. And so therefore I have to sort of keep track of both of those things. And then that'll allow me to continue to apply actions in the state space. But I'm only going to count them if the 1 tile, for instance, is moved. And I will know where the blank is as well. So I will know that I am at a new state, but the heuristic doesn't change as I move the blank around. So this isn't too hard. It should be, hopefully it's not too hard. But what I'm going to show you is that actually this gives us Manhattan distance. Because the idea here is as long as my tiles are disjoint, then I can add them together. So now what I can do is I can think of Manhattan distance we have to build a separate pattern database for every tile, but basically I take the 0 and the 1 tile and I build a pattern with them. I take the 0 and the 2 tile and I build a pattern for them. I take the 0 and the 3 tile and I do it all the way down until I have the 0 and the 9 tile. And what this will give me for any particular state is that this will actually, when I solve this, you give me an arbitrary state in the state space. And here I just had my one I was using up here, whatever, 812045673. 812045673. So if I think about this state in the state space, what am I able to do now? Well, I just go and I look up where's the 1. Here, well, the 1's in the right location. So where's the 1? And I would use this pattern database. And this pattern database only has 9 states in it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 9 times 8. So 72 states in it, 9 locations of the 1, and then 8 locations of the blank for each of those. So there's 72 entries here, and it tells me, essentially, it gives me Manhattan distance just for the 1 on its own. And then this one has 72 states. And it gives me Manhattan distance just for the 2 on its own. This one gives me Manhattan distance just for the 3 and all the way up. And so if I look at this, I have from 1 to 9, but I don't have the blank. So, oh, sorry, that should be 8 down there. That should be 8. So what I have is I have 8 pattern databases times 72 entries. And that should be 576, I think, if I did my math right. So I've got across all these pattern databases, I have 576 states. And that I've done in each of these individual ones, and I add them together and I get Manhattan distance. But the entire state space is 9 factorial, which is 362,880. Now there are, because of the symmetry, we actually can only get to half of those. So that's what, 181,440. Okay, so we've taken our state space with 181,440 states in it, and we've abstracted it into 8 pattern databases, where 8 pattern databases each only have a single tile in them. Each of them has 72 entries, and so with 576 entries, I go from having no heuristic at all to having my Manhattan distance heuristic. And so this is just a small fraction of the entire state space. And if you were to implement the sliding tile puzzle with Manhattan distance and without Manhattan distance, you'd see there's a massive savings that you get from having the Manhattan distance heuristic. And so this goes back now, if we think about Val-Tortes theorem and the generalized Val-Tortes theorem, by building just 576 states of heuristic, we can get very, very significant savings in the search that we use, and particularly in this case because we figured out the disjoint state space and how we can add things together in our disjoint state spaces. So additive pattern databases are, for the sliding tile puzzle, are basically the state of the art still. There's still other enhancements that we can do on top of them, but these are the best heuristics that we can build. And if we were to build 8 of them, then we would equivalently have Manhattan distance. Now, we always can write a program that actually, essentially this heuristic here compresses into a very compact, like we can write a very compact function. So there is a better representation. Instead of just doing the whole search, we could just write it down as given the start and some start and some goal location, we can figure out, oh, it's only going to take 2 moves to get there. And so we could do this a little bit even more efficiently than my 72 states. But if I didn't know anything about my state space, or I didn't want to have to encode that, it all just could fall out of building each of these heuristics and adding them together. Okay, so what additive pattern databases give us is they give us an alternate view of where Manhattan distance comes from, and it's just an additive heuristic. And it's an additive heuristic where we've built one for every set of tiles, but we could, of course, build them for larger sets of tiles. And if we do it for larger sets of tiles, though, we're actually going to capture Manhattan distance. And so what's something that's really nice is when we had our regular pattern databases, as I said before, that we would take Manhattan distance plus another heuristic, maybe, or 2 heuristics, and we would take the max of all of them. When we get into our additive heuristics, we've already captured Manhattan distance here. And therefore, we no longer have to actually do the max of Manhattan distance, but we can simply just add up the values we get in a additive heuristic. Okay, so that is additive heuristics. They are very powerful. And if you want to solve something really, really quickly with the sliding tile puzzle, even on harder problems, then using the additive heuristics is going to be the way to do that. And what we're going to look at is some other, so there's quite a few things we can do on top of this that will further improve performance. And for instance, will allow us to compress down our state space. So we'll be looking at those over the next few videos.